So we often kind of casually talk about the conservation of energy. And while that principle is 100% valid, of course, we often don't really dive deep enough into it to think about, is it always dictate the way things are? So let me give you an example. We talk about how heat transfers from high temperatures materials to low temperature materials. And the heat lost by the high temperature material is gained by the low temperature material. That's conservation of energy. But conservation of energy would also be true if the heat went from the low temperature material to the high temperature material, as long as the amount of heat lost in the low temperature equaled the amount of heat gained in the high temperature. So the reverse is also true from a conservation principle, but it doesn't happen in nature. And so that's what I want to talk about with you today. So this idea that there are certain things that happen in nature that are spontaneous, that are natural. And when we try to do the unnatural, like take heat from a low temperature to a high temperature, we have to do something on that system. We have to add work. Conservation of energy still holds, but it's a different process. All right, that's the basis of the second law of thermodynamics, also affectionately known as entropy. So from a thermodynamic standpoint, the idea is that heat flows from high temperature objects, let's say, to low temperature objects or surround. Okay, so we're going to use objects kind of loosely. And this is the key. This is the key. Heat does not flow naturally from low temperature objects to high temperature. If we wanted to do that, we'd have to do work on the system. And again, and I missed the word naturally here, so I'm going to pop it in there just for clarity. This is spontaneous. This is that sort of natural process. So this is the second law of thermodynamics, said in the form of heat and energy. And we're going to explore that in our study of thermodynamics in a later mini lecture. But there's a more general statement here. And the idea of the second law can be used more generally in other ways that we think about it. And that's this idea and definition of entropy. Now, entropy is a state that matter is in, okay? And it can be described as the state of disorder. Okay, the state of disorder of a system. So I said matter, and matter could certainly be part of it, but of a system, the state of disorder of a system. Okay, so what's an example of this? Let's imagine that you have a container of red marbles, and you have a container of blue marbles. And those are ordered. One container has red marbles, one container has blue marbles. If we put that container of red marbles in the bottom of a jar and I pour the container of blue marbles on top of that bottom of the jar, we're still ordered. But if I start to shake that, of course, what happens? They become intermixed, right? They've now entered a state of disorder. If I continue to shake it, no way can I shake those marbles enough to get them to separate again into red marbles and blue marbles. They will remain in this state of disorder. So that's sort of this idea, to give you a picture frame of what entropy is. And entropy, written in kind of that second law of thermodynamics way, is that systems move, I want to make this move towards higher entropy naturally. another way, natural processes move towards a state of entropy. They move towards higher entropy. This is what is key. If we let things just happen naturally, processes will move us towards an area of higher entropy. So, in terms of heat, that means naturally heat flows from high temperatures to low temperatures. In sort of the general sense, processes move us towards entropy. Right? Good job.